Separable differential equations. A differential equation, dy dx equals f of xy, is separable if you can write it in the form g of y dy is equal to h of x dx. In other words, if you can separate the variables, I have a function of y dy equals a function of x dx. Let's jump into an example. We want to solve dy dx equals negative 4xy squared. First, I'm going to go ahead and multiply by the differential dx. We don't want any differentials in the denominator. So I'm going to have dy is equal to negative 4xy squared dx. Now I'm trying to create a g of y dy equals h of x dx situation. I still have a y squared over here, so I'm going to go ahead and divide by y squared. So I have dy divided by y squared is equal to negative 4x dx. And now what I want to do is integrate both sides. So I'm going to go ahead and rewrite the left side as y to the negative 2 dy, because again, I'm going to integrate this, and then I'm going to take the integral of negative 4x dx. Now on the left side, the antiderivative will be y to the negative 1 over negative 1. On the right side, I'm going to have negative 4x squared over 2. Now on an improper integral, we would have a generic constant, but we're not going to put a generic constant on each side because, again, it's generic. So if I put a plus c over here and a plus d over here, we could combine those together, and really that's still just some generic constant. So we're just going to put the constant on one side, typically on the side of the independent variable. So here that's going to be x. So I'm going to keep that plus c on the right side. All right, now let's simplify this a little bit. So we're going to rewrite the left side as negative 1 over y, and the right side as negative 2x squared plus c. Now here, ideally, I want to solve explicitly, so y is a function of x. So I want to solve for y here. So I'm going to give myself a little bit of space. All right, now I'm going to go ahead and multiply both sides through by the negative 1. So I'm going to have 1 over y is equal to positive 2x squared minus c. Now remember, c is a generic constant, but I don't really like to have this idea of minus a constant, but this would end up being a different constant because we multiplied by a negative. So what we do instead of multiplying through by a negative or even any other coefficient is, if we are performing some operation to c, we just keep it a plus and then change it to a different generic constant. So plus some c1. So instead of calling it c, I'm going to go ahead and call it c1 because it was technically negative c or minus c. All right, so now I'm going to go ahead and solve for y. So this right-hand side, 2x squared plus c1, I can think about it as over 1. And then what I can do is simply take the reciprocal of both sides. Or what I could do is think about it as cross multiplying. Essentially, it's going to turn out to be y equals 1 over 2x squared plus c1. So this is my general solution to my differential equation. Now let's remember what our differential equation was. dy dx was equal to negative 4x y squared. So what we found is that when we substitute this function into y on the right-hand side, and when we take the derivative of this function, dy dx, and substitute it on the left side is going to equal the right side. That's what we're finding. We're finding this function y that satisfies or makes this differential equation true. But there is a more trivial solution. So if we look at this y value over here, and we think about letting y equal 0. Well, if we let y equal 0, and then take the derivative, well, dy dx is also equal to 0. So if I substitute y equals 0 on the right and dy dx equals 0 on the left, I am also going to get a true statement. I'm going to get 0 equals negative 4x times 0 squared, or 0 is equal to 0. So that means y equals 0 is also a solution.
So, in summary, when we solve a separable differential equation, we may not be getting the entire solution set. There might be some constant solutions of the form y equals k that can be found by setting the derivative equal to 0. If you take a full on differential equations course, you'll learn more about what are called equilibrium solutions.
Here are some general steps for solving a separable differential equation. First, separate the variables into the form g of y dy equals h of x dx. Differentials cannot be in the denominator. 2, we're going to integrate both sides. We only need one constant of integration, traditionally on the side with the independent variable. 3, we're going to use the initial condition to find the constant, if applicable. 4, we're going to write the solution explicitly where appropriate and when possible.
And when we start to get into application problems, when it makes sense to solve explicitly.
Let's solve secant x dy dx equals e to the y plus sine x. Let's start by multiplying the differential dx to the other side. So we're going to have secant x dy is equal to e to the y plus sine x dx. Now, on the right-hand side, we're going to use a property of exponents here because I have both a y and an x up in the exponent. I'm going to rewrite this as e to the y times e to the sine x dx. So remember, if they have the same base, we can add their exponents together. So here we're just going the other way around so that now everything is multiplied over here and I can start to move things around and collect my g of y dy and my h of x dx. So on the left, I'm going to leave my dy and divide by e to the y. So I'll have dy divided by e to the y. And then I'm going to leave e to the sine x dx, and I'm going to divide by secant x on both sides. So I'm going to have divided by secant x. So we divided by e to the y, we divided by secant x, so I have all my y's on one side and all my x's on the other side. And so let's get ready to integrate here. So on the left side, I'm going to rewrite this as e to the negative y dy. And on the right side, what I want us to remember is that I have 1 over secant x, and 1 over secant x is cosine x. So what I really have on the right-hand side is cosine x times e to the sine x dx. And now hopefully we can see what integration strategy we would use on the right-hand side. So let's make a little bit more space. Let's work on this right-hand side first. We're going to go ahead and do a u substitution. U is going to be sine x. The derivative of sine x is cosine x dx, which I have right there, cosine x dx. That's why we wanted to recognize 1 over secant x is cosine x. So then the right-hand side just becomes integrating e to the u du. And let's finish that out. That's just e to the u. And we'll put our plus c on that side with the x. And then let's go ahead and replace u with sine. So we have e to the sine x plus c. Now on the left side, the integral of e to the negative y is going to be just negative e to the negative y. So I'm just going to go ahead and bring that answer down here, negative e to the negative y. All right, so now let's go ahead and attempt to solve for y. I'm going to multiply through by the negative. So we're going to have e to the negative y is equal to negative e to the sine x, and then minus c. But again, instead of thinking about this as minus c, I'm just going to call this plus some c1 value. And now to solve for y, I'm going to take the natural log of both sides to get rid of the e in the base. So if I take the natural log of both sides, natural log of e to the negative y, and then natural log of the quantity, negative e to the sine x plus c1. Now on the left, I'm going to just have negative y. I needed a bit more space, so now we have negative y is equal to natural log the quantity negative e to the sine x plus c1, and then we'll multiply through by the negative or divide the negative out. So we'll have y equals negative natural log of negative e to the sine x plus c1. So this is our general solution. Now let's solve the quantity 4y minus cosine of y over 2 times y prime minus 3x squared equals 0. So here, this is written as y prime instead of dy dx. So we want to maybe go ahead and start by rewriting y prime as dy dx. And also, kind of all at one time, I'm going to go ahead and add 3x squared to the other side here. So I want to go ahead and start to think about my g of y dy equals h of x dx situation. So we add the 3y squared to the other side. And so now on this left side, I have this function of y times dy, as long as I go ahead and multiply the dx to the other side. So we're almost separable. We have 4y minus cosine of y over 2 dy is equal to 3x squared dx. And now let's go ahead and integrate both sides. So we'll have 4y squared over 2, and then we'll have minus 2 sine of y over 2. So where's that coming from? Because y over 2, of course, is 1/2 y. And so the antiderivative of negative cosine is going to be negative sine. And then the 2 is the reciprocal of 1/2 here. So we know that when we take the derivative of sine of 1/2 y, a 1/2 would come to the front, so we need that 2 there to cancel it out, right? So essentially it's a u substitution, but just done fairly quickly because the u is linear. And we will not keep the c on the side of the y variable. We'll go ahead and reserve that for the right side with the x. The antiderivative of 3x squared, so that's 3x cubed over 3, and then we'll keep the plus c. So now let's just go ahead and simplify. So we have 2y squared minus 2 sine of y over 2 is equal to x cubed plus c. Now here, we are not going to go ahead and attempt to solve to write y explicitly as a function of x. So hopefully we can see here how complicated even attempting that would be, if that's even possible, because we have y squared and sine of y over 2. So we'll just go ahead and leave our general solution like this. Let's solve dy dx equals natural log x over x times y with the initial condition y of 1 is equal to 2. Let's start by separating the variables. I'm going to do this all at once here. So I'm going to go ahead and multiply both sides by y and multiply both sides by dx. So what I'm going to get is y dy is equal to natural log x over x dx. So again, what I did was multiplied both sides by dx so that the dx is canceled. And then what I also did is multiplied both sides by y. So over here, the y's canceled out. So ideally, we want to do the separation of variables in as few steps as possible so that we can get to the integrating. So now we're going to integrate both sides. On the left, I'm going to have y squared over 2. On the right, this is going to be a u substitution and a fairly straightforward one. So if u is natural log x, du is 1 over x dx, and I have that right here. So now this is really just u du. And that integrates to u squared over 2 plus c. And u was natural log x, so we'll put natural log x in parentheses. All of that is squared over 2 plus c, and that is equal to, if we bring this down, y squared over 2. Now, this time, we have an initial condition. We know that y of 1 is equal to 2. So what I like to do, right when I have integrated both sides and I have my generic constant, I immediately solve for c. So I pull it over to the side, and I remember y of 1 is equal to 2. Now I need a little bit more space. Here we go. So 1 is the input, so that's the x value, and 2 is the output, so that's the y value. I'm going to replace x with 1 and y with 2 to solve for c. So we're going to have 2 squared over 2 is equal to natural log 1 squared over 2 plus c. 2 squared is 4. 4 divided by 2 is 2, so I get 2 is equal to natural log of 1 is 0. So 0 divided by 2 is 0. So I get that the value of c is just 2. Now I'm going to come over here and substitute that in for c. So we get y squared over 2 is equal to natural log x squared over 2 plus 2. And now we're going to try to solve for y. So I'll start by clearing fractions. I'll multiply both sides of the equation by 2. So we're going to have y squared is equal to natural log of x quantity squared. The 2's will cancel out here. Multiply this 2 by 2, so we're going to get plus 4. And then I'm going to go ahead and take the square root of both sides. So I have y equals, and technically what's going to come out is plus or minus, but we'll talk about that in a second. So plus or minus the square root of the quantity natural log of x, still needs to be in parentheses, squared, plus 4. Now, it's only going to be the positive version of this answer, of this equation, because we know that our initial condition must be satisfied. Our initial condition was that y of 1 is equal to 2. So when I substitute 1 into my equation, I have to get out positive 2. So if I substitute in 1, we already said natural log of 1 was 0. So I'm just going to have the square root of 4. And if I want the answer to be positive 2, I have to choose the positive version. So I'll just erase the signs altogether. I just want the positive version of this equation. And that is my final answer. So this is not a general solution. This is the particular solution that satisfies this initial condition. Here let's solve y prime equals xy sine x all over y plus 1 with the initial condition y of 0 equals 1. So first let's recall y prime we can express as dy dx, and then we have equals xy sine x all over y plus 1. So let's multiply by the dx. So we're going to have dy is equal to x times y sine x all over y plus 1 dx. So on the right-hand side, we want to keep x times sine x dx, but we want to go ahead and multiply over the y plus 1 to the other side. So we'll do this in 2 steps. So we have y plus 1 times dy equals x y sine x dx. And then the last step here to separate the variables is to divide both sides by y. So we're going to end up with y plus 1 over y dy is equal to x sine x dx. And now we're going to go ahead and integrate both sides, and we'll need a little bit more space. On the left side, y plus 1 over y, what we can do is go ahead and split it up or karate chop it. So we're going to have the integral of 1 plus 1 over y dy, and then is equal to the integral of x sine x dx. Now the left side, we'll go ahead and finish it out since we started working on it. So here, the integral of 1 is y, and the integral of 1 over y is natural log the absolute value of y. On the right-hand side, this is going to be an integration by parts. So if I let u equal x and dv equals sine x, then I can go ahead and differentiate x, that's 1, and I'm going to use the tabular method or the DI method, and I'm going to go ahead and take the derivative again, which is now 0. And then I'll go ahead and integrate. The integral of sine is going to be negative cosine x, and the integral of negative cosine x is negative sine x. So I integrate until I match the 0 here. And then for this tabular method, the diagonals are going to be the answer, but the signs are going to alternate down these diagonal arrows here. So we're going to just take the signs as they are in this first diagonal because this plus doesn't change anything. So I'm going to have negative x cosine x, negative x cosine x. And then this diagonal here, we're going to multiply in this extra negative. So we're going to end up with a positive sine x. So we're going to have plus sine x plus c. So here is my general solution, but we did have an initial condition. So our initial condition, as a reminder, was y of 0 is equal to 1. So I'm going to move that work over here. I'm going to use my initial condition, y of 0 is equal to 1. I'm going to let the x value be 0 and the y value be 1. So this left side, we're going to have 1 plus natural log 1 is equal to, well, we're just going to have 0 in this first term because 0 times cosine of 0 is 0, plus sine of 0, well, that's also 0, and then plus c. Okay, so natural log of 1 is 0, so here's what I have. C is equal to 1. We'll go ahead and substitute that back in here. So we get y plus natural log absolute value of y is equal to negative x cosine x plus sine x plus 1. And this is, again, our particular solution because we solved for c using our initial condition. Here, let's solve dx dt equals x squared t minus 2x squared minus t plus 2. So here our derivative is dx dt instead of dy dx, which is fine. T is now the independent variable. X is the dependent variable. That's what we are solving for, a function x that satisfies this differential equation. Now, in order to separate the variables here, what we're going to have to do is factor the right-hand side. Right now, it's a bunch of terms that are added or subtracted, and I cannot start to add and subtract them to the other side to separate the variables. We want to, again, turn this into a product, or we would need a product or a quotient in order to start to multiply and divide to the other side. So here, let's go ahead and factor by grouping. So we have these first two terms and these second two terms are going to form our groups. And in the first two terms, we can factor out an x squared. So we're going to have x squared times the quantity t minus 2 is what's left over. In the second two terms, I can factor out a negative 1, and that's going to leave me with t minus 2. So if I factor a negative out of a negative is going to be left over. And so now what's in common, this common binomial, is t minus 2. If we factor that out, we're going to have t minus 2, and then we're going to have x squared minus 1 as our other factor. So here's what we have. We have dx dt is equal to t minus 2 times x squared minus 1. And so we'll go ahead now that we have a product and start to separate the variables. So we'll have our dx on the left divided by x squared minus 1. And then we'll multiply the dt to the other side, and that's going to give us t minus 2 dt. And then we're going to go ahead and integrate both sides. On the right-hand side, we can just go ahead and say that the antiderivative is t squared over 2 minus 2t plus c. But on the left-hand side, we are going to have to factor the denominator and then recognize that this becomes a partial fraction decomposition. So x squared minus 1 is x minus 1, x plus 1. So we're going to have a over x minus 1 plus b over x plus 1 dx. Let's move this over a little bit. All right, so let's go ahead and take this work off to the side to solve for a and b. There are a lot of different ways to do this. What I'm going to do is recognize that in the numerator here, I have just a 1. So what we'd have is that 1 is equal to, if I cross multiply these, I'm going to have this primary equation, a times the quantity x plus 1 plus b times the quantity x minus 1. And then I can let x equal negative 1 and x equal positive 1 to solve for a and b. So if I let x equal negative 1, then I have 1 is equal to, here, this is going to zero out. Negative 1 minus 1 is negative 2, so negative 2b. So b is negative 1/2. And then if I let x equal positive 1, I'll have 1 is equal to 2a. So 1 plus 1 is 2, 1 minus 1 is 0, that zeroes out. So a is positive 1/2. And so remember, we take those back over here, and we're going to integrate now 1/2 over x minus 1 minus 1/2 over x plus 1 dx. Let's make a little bit of space. All right, so now we have 1/2 natural log the absolute value of x minus 1 minus 1/2 natural log absolute value of x plus 1. And then that's equal to, let's go ahead and bring this down, t squared over 2 minus 2t plus c. Now I've made some space because I do want to go ahead and simplify further and try to write x as a function of just t. On the left-hand side, let's notice I can factor out a 1/2. So I'd have 1/2 natural log absolute value of x minus 1 minus natural log absolute value of x plus 1. And now by log properties, I can turn this into natural log absolute value of x minus 1 over x plus 1, still with that 1/2 in front. And then that's equal to, if we bring this down, t squared over 2 minus 2t plus c. Now, we'll multiply both sides by 2 here to get rid of this 1/2. So we'll have natural log absolute value x minus 1 over x plus 1 is equal to t squared minus 4t plus, so this would be 2c. So again, I'm multiplying both sides here by 2 is what's going on. And so the 2 distributed, and now this part right here would be 2c. And 2 times a generic constant is just a different generic constant, so we'll go ahead and make that C1. Now we're going to go ahead and exponentiate both sides. So we're trying to solve for x here, so I'm going to go ahead and exponentiate both sides. So e to the natural log of this absolute value quantity, and then e to the t squared minus 4t plus c1. So now on the left-hand side, e and natural log are going to cancel and give us just absolute value of x minus 1, x plus 1. And then on the right-hand side, here's what I'm going to go ahead and do. This is e to the t squared minus 4t times e to the c1. So what am I doing there and why am I doing it? So remember that this C1 is just some generic constant. And so I'm using my properties of exponents. And so if I have the same base, I can add these back together. So this really is equal to this previous line here. But I wanted to separate out the part that involves that constant. So now e to the C1 is also just some generic constant. So I'm going to go ahead and change that to, let's say, some C2 value. And I'm going to put it in the front. So this is some, let's say, C2, e to the t squared minus 4t. And then we have, this is equal to absolute value of x minus 1 over x plus 1. Whew, okay, need more space. I'm at this point where I have these absolute value bars here. And so what that means is that this is technically going to be plus or minus if I want to drop the absolute value bars. So it's like x minus 1 over x plus 1 is equal to like plus or minus c2 e to the t squared minus 4t, but this is a generic constant, so it's going to absorb the plus or minus. So this is just going to be, potentially some other generic constant. So we're going to go ahead and call it some c3 now. And so I have x minus 1 over x plus 1 equals c3 e to the t squared minus 4t. And now I want to solve for x. So what we're going to do to solve for x is let's multiply the x plus 1 to the other side. So I have x minus 1 is equal to c3 e to the t squared minus 4t times x plus 1. And so this is all one thing right here. It's going to distribute to both terms. So we'll have c3 e to the t squared minus 4t x, and then just plus c3 e to the t squared minus 4t is equal to x minus 1. So we're going to collect like terms. Now I'm going to take this whole term involving x, subtract it to this side, add the 1 to the other side. So I have x minus c3 e to the t squared minus 4tx is equal to c3 e to the t squared minus 4t plus 1. So we left this guy without x's on the right and added 1 to the other side. We'll factor out an x here. And we have 1 minus c3e to the t squared minus 4t is equal to that same thing, c3e to the t squared minus 4t plus 1 on the right. And the final step to solve for x is to divide this quantity to the other side. So we finally have x equals, let's write it like this, 1 plus c3e to the t squared minus 4t over 1 minus some constant e to the t squared minus 4t. There were a lot of important little pieces that went into that. We used a log property, we used properties of exponents, try to understand this idea of eliminating the absolute value bars and the constant absorbing the plus or minus. So a lot of really important parts to pay attention to. Let's solve t plus 2 over y squared dy dt equals 4 over 2t minus 3. So I'm going to go ahead and multiply the dt to the other side. We'll do this in a few steps. So we have t plus 2 over y squared dy is equal to 4 over 2t minus 3 dt. So what do we have to do? We still have to move this t plus 2 to the other side. So we're going to divide by it. So what we're going to have left is a 1 over y squared dy on the left. And then we're going to have 4 over 2t minus 3 times t plus 2 dt on the right-hand side. So now I have my variables separated. We can go ahead and integrate both sides. Now the left side, the antiderivative is just going to be of y to the negative 2 dy. So that's y to the negative 1 over negative 1, or negative y to the negative 1. That's a pretty straightforward one. But on the right-hand side here, we can hopefully see, because it's already sort of set up, it's going to be a partial fractions problem. So it's going to be some a over 2t minus 3 plus some b over t plus 2 dt. And so let's go ahead and set up our primary equation. So we'll go ahead and say that 4 has to equal a times t plus 2 plus b times 2t minus 3. So the original numerator equals the new numerator found by combining these, or just kind of cross multiplying is the shortcut. And so if we let t equal negative 2, then we can solve for b. So if we let t equals negative 2, then we'll get 4 is equal to b times, here, negative 2 times 2, that's negative 4 minus 3, so negative 7. So we get negative 4/7 for b. And then we'll solve for a by substituting in over here positive 3/2. That's what's going to make this factor equal 0. Needed some more space here. So if I let t equal positive 3/2, I'm going to have 4 is equal to a times 3/2 plus 2. 2 is 4 over 2, so we have 7 over 2a is equal to 4. And then if I multiply by 2/7 on both sides, then I'm going to have 8/7 is equal to a. So those are our values of a and b, some fractions. And so we are integrating 8/7 over 2t minus 3, and then minus 4/7 over t plus 2 dt. All right, so we're going to have 8/7 in the front, and then here it is going to become natural log, but because it's not just t minus 3, there's this 2 in the front, we're going to have a 1/2 come out, technically from u substitution, right? So we're going to have 8/7 times 1/2 natural log absolute value of 2t minus 3 minus 4/7. And then this one is just a 1t plus 2. So natural log absolute value of t plus 2 plus c. And that was all equal to, here, let's rewrite this as negative 1 over y. All right, so let's go ahead now and try to solve for y. Let's clean this up a little bit. So I'm going to multiply through by the negative on both sides. So I have 1 over y is equal to, let's see here, 8 over 2 simplifies to 4. So we're going to have negative 4/7 natural log absolute value 2t minus 3. and then plus 4/7 because I'm distributing through a negative, right? This negative is going to distribute through natural log and then t plus 2. And then this, instead of being minus c, we'll just say plus some other c1. And then let's go ahead and remember that all of this is over 1. Needed a bit more space. And so now I can just take the reciprocal of both sides. So I end up with y is equal to 1 all over, and then negative 4/7 natural log absolute value 2t minus 3 plus 4/7 natural log absolute value t plus 2 plus c1. We can clear fractions here. We can multiply the top and bottom by 7 so that we don't have the 4/7 in front. So we can say y equals 7 over negative 4 natural log of 2t minus 3 plus 4 natural log t plus 2, make this bigger, plus some c2, right? Because I'd multiply through by 7, so this is going to technically change whatever this constant was in the previous line. Now there is a little bit more simplifying that I could do here. I could factor out a 4 so that I could combine these logs together. So I could say 7 over, and then if I take out a 4, then I'd have natural log of the absolute value of the positive one would be on top. T plus 2 would be on the top, and then 2t minus 3 would be on the bottom, plus c2. So I'm factoring out the 4, and then that's going to leave me with, natural log of t plus 2 minus natural log of 2t minus 3. And we know that if we subtract two logs, it becomes log of a quotient. But the one that's subtracted is the one that goes on the bottom of the inside, and the one that was added is the one that's on the top on the inside. So this is as nice as we can kind of get it
For our general solution.